Associate Professor of Mathematics in the Department of Mathematics of Higher Teacher Training College of the University of Bamenda in Cameroon. His main interests are in number theory, arithmetic geometry, especially arithmetic of elliptic curves, efficient computation of bilinear maps over elliptic curves, and their application to cryptography. So welcome to the African Mathematics Seminar. So please, Emmanuel.
Okay, thank you. Greeting to everyone. So I would like to say thank you for the invitation to present, in fact, to make myself known on what I'm working. So thank you to Praise and thank you to Prof. Jared of this initiative so that African researchers can meet themselves. So thank you for the presentation too. So I'm going to, it's a basic presentation on the first computation of the finite exponentiation in pairing-based cryptography. So actually, pairings too, we pair two elements. So pairings is a bilinear map that is in the context of cryptography, which is defined over elliptic curve. So, and a pairing of 2 points P and Q is simply this function that we evaluate at Q. We depend on P, and then we raise the results to a power pk minus 1 over r, where P is a large prime number, K is an integer, and R is also a large prime number. So the evaluation of FRP is something else, and then raising the results to the power pk minus 1 over r is what we call final exponentiation. So I'm going to explain or to give details on one algorithm that enable a faster exponentiation in this case. And so to ease my presentation, I will briefly revise what is pairing over elliptic curves. Maybe I will say something about efficient computation of the Miller loop to obtain the value of the function FRP at the point Q that I just showed you. And then I will present some techniques for squaring in a cyclotomic subgroup of the finite field. So what is an elliptic curve? Well, I'm going to present elliptic curve over a field, a finite field, but what I'm going to present is also true over a general field, just that for cryptographic application, we would like to be working over finite field. So if we have a finite field, what we call elliptic curve over a finite field, it's just a plane curve with the projective equation given like this. So with coefficients belonging to the finite field. And this equation is in general known as a generalized projective Weierstrass equation. And you see in this equation, if we set Z to be 0, then we obtain a single point O with coordinate 0, 1, 0 that we will call the point at infinity. And if Z is different from 0, then we can deshomogenize the equation to obtain a Weierstrass equation given like y squared plus hxy equal to sx, where hx and sx are given as follows. So, and in cryptography, we like to have equations which are smooth, and we introduce the concept of discriminant, which is given with which is expressed in terms of the coefficient of the equation like this, and the equation will be smooth if this quantity is different from 0. And also, we can bring a simplified version of the equation depending on the characteristic of the base field. So if the curve is defined over a final field of characteristic different from 2, then we can do a transformation to have an equation in a very shorter form like this, okay? And if furthermore, the characteristic of the equation, or I mean of the finite field is different from 3, we can go further and simplify the equation using this transformation, and we get a very shorter equation in this form: y squared equal to x cubed plus ax plus b, which is called the shorter Weierstrass equation. So if you are working in a field of characteristic different from 2 and 3, then an elliptic curve is simply given by an equation y squared equal to x cubed plus ax plus b. Sorry, there's no equal to 0 here, where a and b in FQ satisfied this condition, this delta different from 0, to ensure that the elliptic curve is smooth. So these are examples of elliptic curves. These examples are, we have here elliptic curves over rails. And then these ones are not elliptic curve because here this point, the discriminant here is equal to 0. Then over a finite field, elliptic curves is something else. You can see, yeah, when the field is larger, so the graph of the elliptic curve is something else. So now, why elliptic curve in cryptography is simply because there is a group structure on elliptic curve, and one may wonder how we can have a group law on the set of rational points of an elliptic curve. I just want in a few minutes to motivate how we have a group law on the elliptic curve. So we introduce the concept of divisor, and we define a divisor as a formal sum, or like this, just a summation of symbols related to points of the elliptic curves, where the coefficients NP are all 0, but not finitely many points. And we can define, we said that the set of divisor, or the divisor group of an elliptic curve, it's simply the free abelian group consisting of rational divisors with the obvious formal addition like this. So if you have two divisors like this, we want to add them. We obtain a third divisor like this. So if P is present on the two divisor, then we just add the coefficients here in the sum. If P is only in one divisor, we maintain it here, and so on. And the degree of the divisor is simply the sum of the coefficient. And we can see that the degree defines a group homomorphism from the set of divisors to Z, because when we take a divisor, the degree is simply an integer equal to the sum of the coefficients. And we consider the kernel of that homomorphism and denote it by div 0, that is the set of divisors, so that the summation of the coefficient is equal to 0. We call it, we denote div O of E. We can also define the divisor of a function over elliptic curve. So if the function is a constant, we assign the 0 divisor. And if not, we define the divisor of f to be this summation, where VPF represent the valuation of f at P. So when this quantity is greater than 0, we say P is a 0 of f. And when it is less than 0, this is called the pole of f. And if we take a smooth projective elliptic curve over a finite field, there are few operations that we can recall. In particular, that the divisor of a function has degree 0, and then the divisor of the product of two functions is simply the sum of the divisors. And we are going to denote the set of principal divisors by pring of x. So as springs of x is an abelian subgroup of div O of x, we take the quotient and form the quotient group and call it the divisor class group of degree 0. And we can prove that miraculously this group is isomorphic to I mean, this is isomorphic to the set of point of the elliptic curve. And so we can transfer the group law. We can transform this to a group homomorphism by transferring the group law here to the set of point of elliptic curve. So there is a geometry interpretation to this. It means, well, that if you have 2 points P and Q on the elliptic curve, and you want to add them, you draw the line passing through P and Q, which intersect the curve at the third point. We can prove it at the third point. And then we take the reflection with respect to the x-axis to obtain what we call the point P plus Q. And then if we want to double a point, that is, we have this point, and we want to do P plus P, then we draw the tangent line to the curve at P, and then it will intersect the curve at the third point. We take the reflection to form the point P plus P. And of course, if we can easily write the equation of these lines, find the intersection, so we can obtain the coordinate of the third point. That is, if we have P of coordinate AB and Q of coordinate CD, by drawing the line, find the intersection, then we'll easily get the coordinate of the third point P plus Q, which are G and H. Good. So now we have over the set of rational point of an elliptic curve. We now know that we can define a group structure, the addition law. And if the curve is defined over a finite field, it means that the corresponding group is a finite group. So if we take R to be a prime divisor if R is the largest divisor of the order of the elliptic curve, then taking a point Q in a subgroup generated by another point P, it means that Q is equal to a certain NP. So when parameters are carefully chosen, it is proven that given Q in the subgroup generated by P, then finding the integer n so that Q is equal to NP, that is P plus P n times, is difficult. And the complexity depends exactly on the largest prime factor of the order of the group. So the problem is called discrete logarithm problem. It's the problem that underlines security of protocols written constructed on the elliptic curve. So one challenge when, as I said here, so the group is suitable for construction of public key algorithm, and challenges include efficient arithmetic of points. So if we are doing cryptography in a structure, we would like to perform operation in a very rapid manner. So it's one of the challenges that I'm not going to really consider here. And still on elliptic curve, there are some other protocols which are very interesting that we call pairings. And I will go straight and explain how to construct pairings over elliptic curves. So we are given an elliptic curve E over a finite field, FP. And then R is the largest subgroup, the largest prime number dividing the order of the group. So we consider this subgroup of the R with coordinate points are with coordinate in FP. And then we consider these other groups with where points have their coordinate in an extension like this. So a pairing is simply a map defined on this product of groups, taking 2 points P, the first one here and the second one here, to a finite field FPK, which is the pairing of P and Q is simply the evaluation of a certain function FRP at Q P is just a function with P of, I'm sorry, where P is a pole, a zero of order R. And to obtain this function when computing pairings, we use a so-called the Miller algorithm. So to obtain this value, we use what we called the Miller algorithm that I'm not going to enter details for now. So this is the Miller algorithm from step 1 to step 9 is to evaluate this function FRP. And then the line 10 here is the raising the results of the Miller loop to the power QK minus 1 over R. And we are interested today on how to perform this operation. So, well, pairings in cryptography would like to have elliptic curves that are suitable for the computation of pairings. Those curves are called pairing-friendly elliptic curves. And for a pairing, a curve to be suitable for pairing computation, we would like K to be small because, you see here, for this operation to be faster, we would like K to be small so that we will not perform too much operations. And we also like, for security reason, the largest prime factor to be greater, the largest prime divisor of the order of the group to be greater than square root of Q. There are various methods and algorithms in the literature to generate pairing-friendly elliptic curve. And some interesting one of them recommends that, prescribe that we can obtain those pairing-friendly curves with polynomial parametrizations. It simply means what? That if you want to obtain an elliptic curve suitable for, that pairing-friendly curves, you can parameterize them by polynomials. It simply means what? That you can generate polynomials P, R, and T, and for a certain value X, so that P is prime, R is also prime, then you can construct an elliptic curve defined over FP, and the order of the elliptic curve has R as a prime factor. So this is an example that I took in the literature called Barrettolin-Scott elliptic curve of with K equal to 48. So if you look, this value X will give you a prime number of 575 prime bits, while R will be a number or a prime number of 512 bits. And in this case, the corresponding elliptic curve is y squared equal to x cubed plus 11. So this is an example of a pairing-friendly elliptic curve. The question now is, if you are to compute pairings over this curve, that is, we are to compute pairings over elliptic curve, then this is what we are going to evaluate. I am not interested today on this expression, but after obtaining this one, how do we raise it to power QK minus 1 over R? So we have this curve. Then the final exponentiation, this expression, because I want to raise the output of the Miller loop to this one, so we divide it, we can split it into this product, that is pk minus 1 over pk, phi k of p. This is the K's cyclotomic polynomial, like this, so that if you take, for example, let me illustrate it with the previous curve. So if you make f to p 48 minus 1 over r, then it is equal to this expression. If you calculate it in this case, you obtain this one. And then the result, this result is going to be raised to power this one. And this expression, it can be easily computed because these are Frobenius, so easy to compute. And then to raise it to power this one will be more complicated. And so to do it, what we do is we take this part of the exponent, we write it to the base p, and we obtain this decomposition where the ki's are given by these relations and so on. So you see that if you take this to raise it to power d, then the number of exponentiation by x are exactly 17, because you first raise it to power k0, and then to power k1, then to power k, and so on up to power k15. The number of exponentiation is exactly 17. So in the previous case, if x is equal to this expression, then it means that an exponentiation by x will cost exactly how many squarings? 32 squarings and just 1, 2, and 3 multiplications. Good. So approximately, if you want to raise this, to make this to this power, the number of squaring is exactly 544 squarings, because you are going to take 32 squaring for one exponentiation times 17. And the cost of squaring, if you take an element of FP in the extension field, FP48, the squaring an element of that field cost exactly 324 multiplication in the base field. So it means that the 544 squarings will cost exactly 1,000, I don't know, is it 1,000, 176,256 M multiplication, 176. Oh, I can't read this in English, I don't know. Well, it costs 176,256 multiplication in the base field. Good. So this is, it shows that when computing pairings in general on pairing-friendly elliptic curve, the final exponentiation step involve lots of squarings. So it's important to look at methods to expedite those computations. So the algorithm I'm going to present shows that the number of squarings, you can reduce the cost up to the half. Okay, so instead of doing thousands of operations like here, we can perform just half of this. That's what I'm going to present now. Good. So our final exponentiation is splitted like this. Then, as in the previous example, it gives this. Then this first part is what we call the easy part. That is, this part is the easy part because it consists of Frobenius operations. Then when you take this result to raise it to power this, it is what we call the hard part of the exponentiation. Good. But a nice observation is that if you take this A and you raise it to power 5k of P, then the answer is exactly 1. It means that A belongs to the cyclotomic subgroup of order this. So if we find a way of computing squarings because the numerous squarings that we are going to perform now belong to the cyclotomic subgroup. So if you find a nice formula in a cyclotomic subgroup to reduce the cost of squaring, it will be very welcome. So how do we deal with this? Well, in pairing-based cryptography, the K that we need are of the form 2 to A times 2 to B. Why? Just because we are going to perform operations in extension fields FPK, and if you have an extension FPK with K written in this form, then you can construct its FPK as sub-extensions of degree 2, 3, 2, 3, where arithmetic will be easy to implement and to perform. So if we take K in that form, and in particular, the case where 6 divides K, then we can observe that this polynomial is exactly equal to this one. And so we will be interested in computing square of elements of FP6 that belongs to the cyclotomic subgroup. So how do we deal with this? So I'm going to explain how to compute an element of FP6 belonging to the cyclotomic subgroup. For that, I'll start with extension of degree 2, then extension of degree 3. So our extension field FQ2 can be constructed easily like this, so that if we take an element in FQ2, this is the standard formula of computing the square of alpha. So that is, you take this element, you raise it to power 2, you write it in the base of FQ2 as a FQ vector space like this. Then you expand it and you get this. And we can see the cost. That is, the cost is just you perform the multiplication AB, and then you perform this multiplication again in FP. So the cost now is 2 multiplication. Now, however, if this alpha that we have just squared, if it belongs in this cyclotomic subgroup of order phi 2 of cure, which is cure plus 1, what does it mean? That alpha to cure plus 1 is 1, or alpha cure times alpha is 1. So we are going to interpret this relation and then put it inside this formula to see if we get a simplification. So then what is alpha cure actually? So if we take alpha, this same alpha, we raise it to cure, is a Frobenius. After little manipulation, we obtain A minus. Okay, we obtain this, that is alpha to cure is simply equal to A minus BX, just a conjugation. And interpreting this relation, that is alpha cure times alpha equal to 1. This is alpha times alpha cure equal to 1. We get A square minus IB square equal to 1. So if you substitute this in the above relation, in the squaring formula, we get alpha square, which is reduced to this simple expression, that is just 2 squaring. In general, we said that here we had a squaring with 2 multiplication, but here now it is reduced to 2 squaring. In general, a squaring is less cost than a multiplication. So we have reduced the cost from 2 multiplication to 2 squaring. But here we cannot see really the difference. Let us move to an extension of degree 6. Then we can construct FQ6 as follows, as an extension of FQ of degree 6, or we construct this as an extension of degree 2, then of degree 3, as given by this relation 2, so that if you take now an alpha, an element in FQ6, it can be written like this: A plus BX plus CX squared, where A, B, and C belong to FQ2, and each A, B, and C can be written also in the basis 1x and x squared, like this. So if we square this formula 8, if you square it in the standard manner, what do we have? We square this, we obtain relation 9. That is, alpha squared is equal to A plus B plus C. I'm going to give the expression of A and B and C. Now we use the fact that alpha belongs to the cyclotomic subgroup. If it belongs to the cyclotomic subgroup of order phi 6 of cure, which is cure square minus cure plus 1, it means alpha to this is equal to 1. In other words, alpha to cure square times alpha is equal to alpha cure. What is alpha cure? It's a conjugation. We can evaluate it and get this expression, and then this is alpha to cure square, and we expand all this, and after simplification we get relation 10, which shows that the product BC can simply be expressed in terms of the basis elements or the generator elements, and D squares, A squared, B, C squared, and B squared. In other words, the original formula of alpha squared, which is regrouped as A plus BX plus CX squared with A, B, C, given like this, we can simplify them to these expressions because we got BC, AB, and AC from the membership relation of alpha to the cyclotomic subgroup. So we get now A, B, and C as 3a squared minus this, 3ic squared, 3b squared minus this. So to compute alpha squared, we simply need to compute a squared, c squared, b squared. It means that the computation of alpha squared, which is the cost of computing alpha squared, which is the cost of computing A, B, and C, it's simply the cost of computing A squared, C squared, and B squared. And remember that A, C, and B belong to FP squared. So one cyclotomic squaring here is just 3 squaring in the extension FP2. And remember that in the extension FP2, a square costs exactly 2 multiplication. So this 3 squaring costs a total of 6 multiplication. So we can summarize it here, and So we have seen that if we are working an extension FP6, then the cost of squaring was exactly 3 squaring in FP2, which is 6 multiplication. And the classical method of computing a square in FP6 costs 12m, the earlier method I just explained. So you see that we are moving from 2 multiplication to 6 multiplication, just because here, in this case, we consider that the squaring that we are performing is in a cyclotomic subgroup. So this is what I wanted to present in the context of exponentiation for pairing-based cryptography. So the conclusion is, to perform the exponentiation in pairings, we have to take note that the squarings in the hard part of the exponentiation are taking place in a cyclotomic subgroup. It enables us to reduce to the half the cost of squarings there. So this formula has been have been derived in the case where K is of the form 2 to A, 3 to B. People are still thinking, if now assume that B is equal to 0, so the formula will not really work. So looking at similar formula, when K is, for example, equal to 8, 16, and so on, can be, I think, will be relevant, because elliptic curve are defined over F16, like what we call KSS curve, elliptic curves, have shown also an interest in pairing-based cryptography. And I think if we improve also the computation of cyclotomic squaring there, it will be a plus. So thank you for your attention. I can now take questions or comments.